When you are given a cyclic structure and you are asked to determine the number of proton NMR signals, the first thing that you need to do is locate all the hydrogens that you have in your structure. So go ahead and draw the stereochemistry of all the hydrogens in there. So I have a hydrogen here which is behind and the hydrogen here which is in front. This is going to be the first step. The second step is I need to locate the different hydrogens, meaning the hydrogens that are connected to different groups. Okay, so if I am looking at the hydrogen here that belongs to the CH3, of course it's going to be different than the hydrogen that is connected to this carbon over here. So these two are two different hydrogens over there. And then if I look at the connectivity over here, this hydrogen is connected to a CH3, which is different than this hydrogen over here, which is connected directly to the carbon of the CH3. Then I would end up having this third hydrogen to be different in this case. I'm going to label those as A, B, and C. So far I have three different types of hydrogen. So the first thing that you need to look for is the connectivity. Now, after you look for the connectivity in there, now I'm going to look for the hydrogens that belong to the same carbon and see if now they belong to the same environment or not. See if they are the same. There are two ways. Either you replace each one of them by an X atom and see if both replacement lead the same compound. For example, I can replace each one of them by a chlorine. So you take that same structure over here. This is going to be the CH3, and this is going to be the CH3 over here. And we're going to replace the first hydrogen by a chlorine and the second hydrogen by a chlorine. And we're going to see if we're going to have the same compound in there. It is the same because if you take a look, this chlorine is cis to this CH3 and it's a trans to the CH3. And this chlorine is cis to the CH3 and it's trans to the CH3. Those two CH3s are the same because the connectivity is the same. So this means that the two chlorines are the same. So this means that the two hydrogens are the same. So this is going to be hydrogen C and this is hydrogen C. This is one way of doing it. Taking the hydrogen that belong to the same carbon and replacing it with an X atom. And seeing if you are going to lead the same compound or mirror images. Then these two are mirror images in there. So this is why we say that these two atoms are equivalent. Another way is to look at the hydrogen itself and see if it is cis or trans to the same group. If it's cis or trans to the same group, then they are the same. And if they are cis and trans to different groups, then they are different. So for example, for HC, let's highlight HC. HC is going to be trans to this hydrogen. And HC over here is a trans to this hydrogen. So these hydrogens are the same. So this is why HCs are the same. So over here, I do have three different sets of hydrogens. This is going to be B and this is going to be A. So I have three different sets of hydrogens. So I have three proton NMR signals. Let's have another example. Now, in this other example, I can simply draw a plane of symmetry in there. Okay? And drawing a plane of symmetry, then I'm going to end up having, for this carbon over here, these two hydrogens, I have a hydrogen here and I have a hydrogen there. Okay? And then go ahead and draw your hydrogens here. So I do have a hydrogen here, and I have a hydrogen over here. Now you can see over here that we have also three sets of hydrogens now. I do have in CH3, this is hydrogen A, this is hydrogen B, and that is going to be hydrogen C as well. The connectivity is different. So there is a difference between hydrogen A and hydrogen B and hydrogen C. But this is going to be the same over here. This is going to be hydrogen B, this is going to be hydrogen C, and this is going to be hydrogen A. So again, I'm going to end up getting 3-proton NMR signals. For the methyl cyclopropane, I can draw a plane of symmetry that passes through the CH3. So here I do have a hydrogen, and then I do have my two sets of hydrogens that are, so I have hydrogen here, and then I do have hydrogen here, and I have hydrogen here as well. Is going to be a set of hydrogen. This is going to be the HA. This is going to be HB over here, okay? And then there is a difference between this hydrogen and this hydrogen. So this is going to be an HC. If I replace this hydrogen by chlorine, then the chlorine is going to be trans to the CH3. And if I replace this hydrogen by chlorine, then the chlorine is going to be cis to the CH3. Now there's a big difference between both. So this is why I'm going to end up having an HD over there. Since I drew a plane of symmetry, this is going to be HC, this is going to be HD. So I'm going to end up having 4 proton NMR signals. For the methyl epoxide, we're going to do exactly the same and to draw all the hydrogens in the structure, and then try to see if they are in equivalent environment or not by replacing them with an X atom. So this CH3 over here, first check the connectivity. Before replacing, check the connectivity. So this CH3 is proton A. Definitely this hydrogen is different, then it is going to be proton B in there. And this hydrogen over here is different, so it's going to be proton C. So now the question is this hydrogen, which is proton C, the same as this proton over here? Go ahead and replace. So if I replace this hydrogen by chlorine, then the chlorine is going to be cis to the CH3. And if I replace this hydrogen by chlorine, it's going to be trans to the CH3. No, they are different. So this is why I'm going to end up having 4 proton NMR signals in this case for this structure. For this is dichlorocyclobutane, there is a plane of symmetry. So we're going to go ahead and draw a plane of symmetry in there. This means that all the hydrogens on one side, they are equivalent to the hydrogens on the other side. Okay, so let's go ahead and draw all of these hydrogens and see if the hydrogens are the same. This is a hydrogen and this is a hydrogen here. So I know that the hydrogens on this side, they are the same as the hydrogens on the other side. Now let's figure out the number of different protons in the structure. So this is going to be hydrogen A, this is going to be immediately hydrogen B. And the reason why, because the connectivity is different, then they are different. The question is, are these two hydrogens the same? Okay, this is the question. So again, go ahead and replace each of these hydrogens with an X atom, like a bromine, for example. So if I replace this hydrogen with the bromine will be cis to the chlorine. The bromine here will be trans to the chlorine. So this means that these two are going to be different. If they are cis or trans to different groups, then they are different. So here I do have 3 sets of hydrogens. And of course, their mirror image is going to be hydrogen C, it's going to be hydrogen B, and this is going to be hydrogen A. So I'm going to end up having 3 proton NMR signals for this structure. For the trans, we're going to do exactly the same. So write down all the hydrogens. And then look at the connectivity. And then look at the connectivity. So I have hydrogen A. I do have hydrogen B over there. So definitely A is different than B. So go ahead and replace these two hydrogens by chlorine, similar to this case over here, or by a bromine. And this hydrogen is going to be trans to the chlorine. This hydrogen is going to be cis to the chlorine, or this group is going to be cis to the chlorine. The cis and trans are different, so this is why hydrogen B is going to be in a different environment than hydrogen C. This means that hydrogen B and C, they split each other. So here I have different sets of hydrogens. Do the same thing on the side, and you're going to see that this hydrogen over here is going to be the same as hydrogen C. This is going to be the same as hydrogen B, and this is going to be the same as hydrogen A. The reason why, because these two hydrogens are the same because they are connected to the same atom, okay, or the same group. Hydrogen B also is going to be the same as this hydrogen B because it's connected to the same group there. It's a carbon Cl, carbon Cl, okay? And then between B and C, we're going to do exactly the same and replace the hydrogens by a group. So this hydrogen is going to be replaced, for example, by a bromine. Bromine will be trans to the chlorine. Bromine here will be cis to the chlorine. Those two chlorines are the same. So this means that the hydrogens are going to be the same, and I'm going to end up having 3 proton NMR signals. Now for this structure over here, there is no plane of symmetry for this structure. Go ahead and draw all the hydrogens that you have, and look, of course, first for the connectivity. So I have a hydrogen here and I have a hydrogen there. Of course, the hydrogens that belong to the CH3, so it's going to be proton A. So the question is, are these two hydrogens the same? They are the same because they are connected to the same group. So this CH3, or this hydrogen here, is adjacent to the O, to the CO. This is exactly the same thing. So these two are going to be in equivalent environment, so they are not going to split each other. They belong to the same carbon in there. Now, coming to this hydrogen over here, there's a difference in the connectivity between these two hydrogens and these two hydrogens. So I'm going to term these two hydrogens B, and I'm going to term these two hydrogens C over there. The question is now, are these two hydrogens the same? So is this an HB and is this an HC? So again, replace with a group, any group. So if you replace this hydrogen with a chlorine, then that chlorine, notice that the CH3s here are the same. So if they are the same, and if I want to replace any one of those by the chlorine, they're going to be cis and trans to the same group. So they're going to be the same. So this is why this is going to be HB, and this is going to be HC. And I have here 3 different proton NMR signals. If you have a cycle which is not substituted at all, then in this case, all the hydrogens, they belong to the same environment. And if they belong to the same environment, they will not split each other. So notice here that all of these hydrogens, because I can draw a plane of symmetry, they do belong to the same environment. So we all have over here just one type of hydrogen, which is hydrogen A for all of them. So this means that hydrogen A's are not going to split each other. So when you look at the signal for this structure in the proton NMR, you're going to see that you're going to have one proton NMR signal, and it's going to be a singlet. It's not going to be a triplet. So you cannot say that this hydrogen or a multiplet is connected to a CH2 on the side and a CH2 on the other side. No, because you can simply draw a plane of symmetry in here anywhere throughout the molecule. So you have only one type of hydrogen, and the same types of hydrogens, they can never split each other. So you're going to see a singlet in here. Same thing for the cyclohexane. You have only one type of hydrogen among all. So also you're going to see there's going to be hydrogen A, hydrogen A, hydrogen A, hydrogen A. Same thing. So you're going to see only one proton NMR signal, and it's going to be a singlet.